For 2 months, I've been working on a video with the working title, Should We Defund Academia? Well, reality is moving faster than me. Thanks to Donald Trump and Elon Musk, I might have to rename my video to Was it a good idea to defund academia? So many things have happened in the past 2 weeks. Here is my 5-minute summary and a few comments. Trump's actions are not directly aimed at academia. Instead, he's targeting initiatives to improve diversity, equity and inclusion, DEI for short, which Elon Musk has referred to as a woke mind virus and which has become widespread under the Biden administration. Americans have used this term to broadly describe all actions that aim to increase the share of currently underrepresented groups in certain professions, which can lead to less qualified people getting hired or funded. Directly after his inauguration, Trump issued an executive order titled Ending Radical and Wasteful Government DEI Programs and Preferencing, which says that to the maximum extent allowed by law, each federal agency must eliminate all federal DEI and environmental justice officers, positions, actions, initiatives, programs, grant contracts, and performance requirements. On January 21st, he followed up with an order aimed at private business titled Ending Illegal Discrimination and Restoring Merit-Based Opportunity. It encourages the private sector to end illegal DEI discrimination and preferences and says that DEI is dangerous and can violate the civil rights laws of this nation. Briefly after this, agencies such as the Center for Disease Control, CDC, and the National Science Foundation, NSF, were removing datasets from their websites. According to AP, more than 8,000 websites and 3,000 datasets disappeared, mostly concerning public health and environmental studies. The medical advocacy group Doctors for America quickly sued, claiming that the removal prevented doctors from efficiently fighting disease. Last week, a Washington judge issued a temporary restraining order and said the agencies need to restore all relevant information. Next, on January 26th, Trump ordered the shutdown of USAID, an agency with 10,000 or so employees, which mostly funds food and humanitarian assistance across the world. The order says, quote, the United States is no longer going to blindly dole out money with no return for the American people, end quote. The same day, workers pulled down the agency's letters from the Washington building. USAID, however, also finances research at American universities. Those who had been awarded grants made financial commitments and were understandably distressed that the money might not come in. Employees of the agency weren't amused either and immediately sued the Trump administration. A day later, a federal judge in Washington ordered a temporary halt to the USAID shutdown proceedings. Meanwhile, in response to Trump's orders, on January 27th, the Office of Management and Budget temporarily paused all academic grants to allow federal agencies to identify all activities that may be implicated by Trump's previous executive orders, including but not limited to financial assistance for foreign aid, non-governmental organizations, DEI, woke gender ideology, and the Green New Deal. As a result, the National Science Foundation and other federal agencies have been reviewing thousands of research projects. The list of words that'll get you flagged was leaked on Twitter last week and includes terms such as bias, cultural differences, status, trauma, systemic, and women. In one case, a paper on the US Mpox outbreak response, which had just been accepted for publication, was withdrawn upon request by the CDC because, quote, it was not aligned with the president's executive orders, unquote. In another case, a paper on the effects of fentanyl on HIV was put on hold because it contained the word gender. Maybe we should just write papers in emojis. Next, Trump came for academic overhead costs. These are the expenses that are added on top of a research grant and that finance administrative services that the hosting institution provides. That's everything from office maintenance to IT support. In the US, it ranges between 30% and 70% of a grant's total value. The Trump administration kept the overhead at 15%, which would save an estimated $4 billion. This decision, too, was quickly blocked by a federal judge on the grounds that it had cut into the very infrastructure that supports groundbreaking research. Personally, I think the major problem here isn't the goal of the Trump administration, but their means to reach that goal. I'm afraid that the current procedure is lumping legitimate and nonsense research together indiscriminately. And while I've myself criticized research overheads that are almost certainly the major contributor to university admin bloat, and many private funders do put a 15% cut on overhead, for example, the Templeton Foundation, this isn't a change that an institution can implement on the snap of a finger. Never in the history of universities have they implemented anything on the snap of a finger. At this rate, I'll soon have to rename my video to Remember When We Had Academia? The incoming CERN director recently said that the LHC upgrade could show us how the universe will end. That's quite an upgrade because so far it's merely been showing us how particle physics will end. But let's have a look at what this is all about. CERN, host of the currently largest particle collider in the world, the Large Hadron Collider LHC, will get a new director next year, a British experimentalist by the name of Mark Thompson. In an interview with The Guardian, he said that there's a particular measurement about the Higgs boson that's so fundamental to the nature of the universe, which is when the proton collisions produce not one Higgs boson but two Higgs bosons at the same time. The Guardian explains that this could reveal whether the Higgs field has reached a final stable resting state or whether a drastic transition could occur in the future, a scenario that would see the universe as we know it evaporate almost instantaneously. What he's talking about is the stability of the vacuum. That's the empty space underneath all the particles that matter is made of. We usually think of the vacuum as nothing, but particle physics has taught us otherwise. What we call the vacuum is really filled with the Higgs field. The Higgs field should not be confused with the Higgs boson. The Higgs field is an even condensate that forms in the early universe and that gives masses to particles by dragging on them. The Higgs boson, on the other hand, is a ripple on top of the condensate, metaphorically speaking. The reason we usually talk about the Higgs boson is that it's the only way we know how to confirm the presence of the field. This is why the Higgs boson discovery in 2012 was such a big deal. The Higgs boson has a particular property known as the self-coupling. That's basically what the name says, the strength by which it interacts with itself. It's a parameter in the standard model that isn't very well known because the best way to infer it is from proton collisions that produce two Higgses, as Thompson said. You see examples of this in these diagrams. Going in left are two gluons which come from the protons and are marked with a G. Then there's stuff going on in the middle with top quarks, and out come two Higgs bosons which interact with each other. It's been somewhat controversial whether the LHC would be able to measure this coupling, or whether the signal would just drown in noise. I'm guessing this is why Thompson is stressing in the Guardian article that AI is going to help and why he says, "Now I'm confident we're going to make a good measurement." This Higgs boson self-coupling now is one of the parameters that determine the stability of the vacuum. By the presently possible estimates, it looks like the vacuum around us is very long-lived but not totally stable. It's a meta stable state, as physicists say. This is much like if you shine light on a phosphorescent material. It'll kick an electron into an energy level where it can remain for some time. But ultimately, that state isn't stable, so the electron falls back down into a lower energy level that emits a photon, which is why these materials have a long afterglow. If our vacuum is also metastable, it'll eventually decay into a state of lower energy. But the excess energy that's released in that process will not just create a nice little glow, it'll tear everything apart. But current estimates say that the half-life of the vacuum is extremely long, about 10 to the 500 years, and by that time all stars would have burnt out and collapsed to black holes, and even the black holes would have evaporated. However, this being a quantum process, there's a small probability that it happens any day now. But don't worry, we'd all be dead before we even knew what was happening. By the way, this video comes with a quiz that lets you check how much you remember. I find Thomson's statements interesting for two reasons. One is that this measurement of the Higgs self-coupling is the biggest selling point for their next bigger particle collider. So now he's basically saying they don't need the bigger collider. It's their biggest selling point if you leave aside the ones that they've made up, like that the next bigger collider would tell us something about dark matter or dark energy and other nonsense. The other reason it's interesting is that Thomson seems to agree with me that the next bigger particle collider will not discover any new particle. This is because to believe that the Higgs self-coupling tells you something about the stability of the vacuum, you need to assume that there are no other particles to be found. If there were any, these would also enter the calculation. It's somewhat surprising in that I don't know any other particle physicist who actually believes that. This makes me suspect it's not what he meant to say. I suspect he either doesn't know how the calculation works, or he was sure that no one who knows how it works would mention this little problem. But that's what you have me for. In summary, particle physicists are trying to measure how the Higgs boson couples with itself. Regardless of what they measure, this will not tell us how the universe will end. And they still haven't learned that each time they lie to you, I'll be here to call them out on it. The way people think I make videos is that I wake up in the morning, look up some cool science news, talk about it for 5 minutes, done. The way it actually works is that I sort through 1,000 crappy press releases and then despair over something like quantum mechanics experiment measures a pulse of light in 37 dimensions. I've no idea what that means. But after thinking about it for a week and several existential crises, I believe I've figured it out. So here's my 5-minute summary. The authors of this new paper have found theoretical and experimental proof that quantum mechanics is weirder than we thought, not just verbally, but in a quantifiable way that could be used on quantum computers. It's actually pretty cool, and it gives me an opportunity to explain how superdeterminism works. In the new paper, they study a variant of a problem known as the GHZ paradox. It's nothing to do with gigahertz, but stands for Greenberger-Horn-Zeilinger. For this, you need 3 quantum particles that have at least 2 different properties. Typically, one uses electrons and measures their spin in 2 different directions, say horizontally and vertically. An electron is really just a tiny spinning ball, except it's not a ball and it's not spinning, which is hard to draw. So I hope you'll excuse that I'll use coins for illustration instead. These coins have 2 properties that correspond to the electron spin in 2 different directions. Let's say they're either red or blue, and they have +1 on one side and -1 on the other. We'll measure either their color or what side is up. In analogy with the electron spins, we say that if the coin's red, we'll count this as a +1, and if it's blue, we'll count this as a -1. If the coin lands on an edge, we'll just pretend it didn't happen. For this quantum paradox, one needs 3 of these coins. We throw them on the table and then we make measurements on them. A possible sequence of measurements is that we measure the color of the first coin and the sides of the 2 other coins. For each of these measurements, we get a result that's either +1 or -1, and then we multiply them. Here is an example for the first set of measurements. Let's say the result is +1. We then make 2 further measurements in different combinations, and let's say the result is also +1. This doesn't have to be the case, but it's a possible outcome, and it just makes things easier to look at this particular example. You can see that in this sequence, all the side measurements appear twice. This means that if we multiply all the measurement results, the side measurements will square to 1, regardless of whether the +1 or minus sides were up. So from the previous 3 results, we always know that multiplying all 3 color results will also give 1. And we can also see this in our table. The problem is that if you actually make this experiment with electrons and their spin, the result is -1. This is the paradox. There's no combination of coin results that can give you the result we actually observe. So what's going on? The problem with our calculation is that we assume that the coins have values that are either plus or -1, and that these values don't change if we make further measurements. Take, for example, the second coin. What we measured here is first which side is up, then the color, and then again which side is up. This means we assumed that the side doesn't change if we measure the color. But electrons are quantum particles, and for quantum particles, measuring one thing like the color can change something you already measured previously, like the side. Or to go back to the electron, measuring the spin in one direction makes the spin in the other direction maximally uncertain. Therefore, if you use quantum mechanics to calculate the result of the 4th measurement, you get the correct answer that agrees with observations. Loosely speaking, this is because if you multiply these measurement results in quantum mechanics and want to remove the ones that square to 1, you need to change their order. And if you do that in quantum mechanics, this can bring in a minus. But the most interesting thing about this paradox is that the final result, the -1, is not probabilistic, it's deterministic. It follows from the previous ones. Once you have the results of the first 3 measurements, you know the result of the 4th. And this has practical use. It means that if you can generate 3 electrons and make those measurements, that'll always and reliably produce this weird quantum state. And it's this quantum weirdness that gives quantum computers their extra edge. This is why physicists are so keen on finding reliable ways to generate it, because it means additional computational power. And this finally brings me to the paper with the 37 dimensions. The authors first provide mathematical proof that to find this reliable quantum weirdness, one doesn't need 4 measurements to find a contradiction, as we did. They say one could do it with merely 3, and then they experimentally construct a way to do this. This is where the 37 dimensions come in. These are not dimensions of space, like space around us. The 37 dimensions are the dimensions of the Hilbert space for 6 photons. This means basically that taken together, the photons have 37 different measurable properties: polarization, phases, intensity, and so on. So it's not as mysterious as it sounds. Sorry. But isn't this always the case with quantum physics, that if you look at the maths, it's not as mysterious as it sounds? Why 37? That's just the lowest number of dimensions that they found to work. Maybe tomorrow someone will do it in 19. And no, I'm not going to draw you a table in 37 dimensions. I have my limits. Let me instead add some comments on what this is all good for. The advantage of quantum computers comes from them having properties that a non-quantum system can't have. And these paradoxical GHZ states are a great example for this, because if you know how to generate them, they're so reliable. And the fewer measurements you need to make, the more efficient your calculation becomes. and 3 is less than 4. On the flip side, you now have to deal with these 37 dimensions, so don't expect this to go into mass production tomorrow. On a more practical note, if you're working on your own theory of quantum physics, and I know there are quite a few among you who dream of that, you need to come up with a way to obtain the correct results for the GHZ experiment. And then let me finally say some words about how superdeterminism explains the quantum mechanical result. Superdeterminism is an unfortunate term that John Bell used to describe what he thought was an implausible explanation. What it really means is just that the probability of a measurement outcome depends on what you measure. In the GHZ table, this means that, for example, the result for the side of the second coin in the third measurement can differ from the one in the first measurement because the measurements on the other coins are different. The result depends on the context. The benefit of superdeterminism, and the reason why I'm convinced it's the correct explanation, is that it's local and therefore compatible with Einstein's theory. Superdeterminism has no spooky action at a distance. Indeed, we know from Bell's theorem that it's the only way to make sure the results of quantum mechanics are compatible with Einstein's locality. Many people don't like this explanation because they think it's constraining their free will or something. But the way that I think about it is that it's just a consistency requirement. And yes, I'm working on a few more papers about this. It's just that these videos keep getting in the way. But hey, at least we learned something. At the very least, how to give Sabine an existential crisis. Just a few days ago, Microsoft announced they'd made a major breakthrough in quantum computing. They said they'd achieved the first step for a scalable platform that could bring us to 1 million qubits quickly and unleash the power of quantum computing onto the world. I've had a look. On February 19th, Microsoft introduced Majorana 1, which according to their press release is the world's first quantum chip powered by a new topological core architecture. With this, they say they expect to realize quantum computers capable of solving meaningful industrial scale problems in years, not decades. The CEO of Microsoft, Satya Nadella, further wrote on X Twitter that they could make this work because after a nearly 20-year pursuit, they've created an entirely new state of matter and that they now have a clear path to a 1 million qubit processor. At the same time, the Microsoft team also published a paper in Nature and a roadmap on the archive. The news made international headlines quickly. Okay, let's unravel this. Quantum computers can solve certain mathematical problems much faster than a conventional computer, at least in theory. In practice, the already existing quantum computers are so small they can't do anything of practical use. Quantum computers operate on quantum bits, qubits, and estimates say that for practical uses we'd need to reach about 1 million qubits. In reality, we're currently at 150 or so useful qubits. I say this so carefully because there are chips with more qubits than that, but I've seen no evidence that they can actually calculate with all of them. There are many different ways to create qubits, and at the moment there's a lot of competition between them. Microsoft in particular has worked on topological quantum computing, which is the past lead taken and also what the new announcement is about. Google and Nokia are also working on topological quantum computing, but progress has generally been slow. For topological quantum computing, you need quantum states whose properties are protected by conserved geometrical features. Topological quantum states are emergent. They don't exist as properties of particles like, say, spin, but they're properties of many interacting particles. To create a topological qubit, you need to find a suitable material and a suitable configuration in which you get these conserved states. This has proved to be extremely difficult, but the nice thing about topological qubits is that because their features are conserved, they're very robust mass to noise. Microsoft uses a particular type of topological state called a Majorana zero mode, after which their new computing platform is named. To create these states, Microsoft uses topological superconductors, which are not a new discovery. They're also not a state of matter, but rather a quantum phase of the solid state. Though, to be honest, this is picking on words. Personally, I don't mind if they call it a state of matter, but I'd object to calling it a new state. New is that they claim that they now have something to actually calculate with. In their new Nature paper, they report that they managed to create such a topological qubit with two different states that are parity states, and that they could measure and distinguish these two different states with 99% reliability. This is pretty good. They did this with tiny aluminium wires cooled to about 50 millikelvin. However, to demonstrate that you have a topological qubit, you don't just need to show that it has two states. Other qubits also have that. You need to show that you can perform operations on the qubits that are protected by the topological properties. That is, they've shown that they have a qubit. They've not shown that it's topological. A lot of physicists are skeptical about this after a Microsoft team published a paper in 2018 that was retracted in 2021. The authors admitted to having made mistakes in their data analysis and presentation. According to a Nature news piece that accompanied the new Microsoft paper, Stephen Simon from the University of Oxford said, "Would I bet my life that they're seeing what they think they're seeing? No, but it looks pretty good." And I think that's a fair summary. Yes, it really is good news and it looks very promising, but the news isn't remotely as big as the headlines made it appear. As to the Microsoft roadmap, it basically says that once they have one qubit, they'll put a lot of them together. The problem with doing that is that you need to still cool them all to a few millikelvin, and the larger the qubits are, the more difficult this becomes. But based on the Microsoft roadmap to quantum computing, I can now give you a scientifically accurate roadmap to becoming a millionaire. Step 1, make $100. Step 2, repeat step 1 10,000 times. When I first talked about the return of supersonic passenger flights some years ago, few wanted to believe it. Too expensive, too loud, look at what happened to the Concorde, and in any case, think about the carbon footprint, it won't happen. But a lot of things have changed in the past years. Or have they? Elon Musk thinks that one day we'll travel by rocket, shot around the globe in his Starship that could bring you from London to New York in 30 minutes. And you know what? I can actually believe that one day this might indeed work. But for the time being, rockets don't land at airports, and most of us can't even afford extra legroom in economy, so it'll be some time until we hop on Elon's rockets. Supersonic airplanes, those that fly faster than the speed of sound, have the advantage that they integrate more easily into passenger travel. The major problem is that the faster you fly, the more air resistance you have to overcome, and the more fuel you need. This makes supersonic flight expensive. Another issue is the supersonic boom, a shock wave that trails behind the airplanes as they fly. It's an issue because, most people don't like it if the 5 a.m. flight blasts the morning coffee into their face. But fuel efficiency has much improved in the past 50 years, and NASA, among others, has developed a smart wing design that can reduce the supersonic boom. And so in the past decade, we've seen several startups trying to bring supersonic passenger flights back. It's been tough going. The American startup Ariane Supersonic shut down in 2021 after they failed to secure the capital needed to begin production of their aeroplane. Another startup, Exosonic, shut down last year for the same reason. There are evidently too few investors willing to put money into the business because it's questionable whether it'll ever be profitable. A company which has survived so far is Boom Supersonic, Supersonic, also based in the United States. They recently made headlines for the first test flight of a civil supersonic passenger plane since the Concorde was retired in 2003. On January 28th, they successfully tested Baby Boom, which sounds like a drum set for toddlers, but is a small prototype of their planned supersonic aeroplane Overture. Baby Boom reached Mach 1.2 in a test flight above the Mojave Desert in Southern California. The company hopes to complete construction on the full-size passenger plane Overture by 2029. Their plan is that it can carry 64 to 80 passengers at Mach 1.7, about twice as fast as commercial airplanes currently are. They have more than 130 orders for aircraft from several major airlines, including American Airlines, United Airlines, and Japan Airlines. According to people watching the test flight, the supersonic boom wasn't audible on the ground due to the high altitude the plane was flying. This is a phenomenon called the Mach cutoff. It works much like a mirage in the desert, just that instead of light, it's sound which is reflected back up. However, this Mach cutoff only works up to speeds below roughly 1.7 Mach, which is why Boom wants to stay below this. The exact cutoff depends strongly on temperature and pressure conditions in the atmosphere. Boom says that thanks to what they call the boomless cruise technology, probably a combination of measurements and machine learning, they're able to calculate the most quiet path, though I suspect what they actually calculate is the path of least complaints. Boom's successful test flight, I imagine, must have been a much celebrated success after their previous setbacks. They originally worked together with Rolls-Royce on the engine development, but in 2022 Rolls-Royce pulled out of the project. They got a no from several other companies, but eventually settled on using 3 engines from General Electric. Still, they had to raise further funds to be able to build their full-size project. The company has seen no end of skepticism and suspicion, like people on Hacker News saying that their demonstrator project is obviously a scam, and many questions about whether they'll ever be economically viable. The company says that Overture is being engineered to run on up to 100% sustainable aviation fuel, but that will only make it more expensive. Besides the finances, the other big investor worry is regulations. Outside of test flights and military purposes, supersonic flights are currently forbidden above populated areas, regardless of how much noise can be heard on the ground. This doesn't make much sense, which is why in 2023, the US Federal Aviation Administration proposed to update the rules for supersonic testing and certification. Another agency works on global standards, and Elon Musk has announced he'll personally get it done. Bringing back supersonic flight has so far mostly been an American enterprise, though there have been some rumors that China made test flights and a Russian company has presented some demonstration technologies. In the United States, besides Boom Supersonic, the most notable companies are currently Spike Aerospace and Hermes. If their vision becomes reality, the future of travel will be supersonic for the 1% and sardine class for the rest.